going to talk a bit about Azure Cosmos DB for PostgreSQL, which is a service that we launched in October. It's a distributed relational database management service built on open source Postgres and Citus. So we've set ourselves a rule, which is don't fork Postgres. It feels good at first, but after a few years, you're going to regret it, and it probably takes a few years to build a distributed relational database. So we just run vanilla Postgres, but with extensions, and you can do a lot with extensions in Postgres. So on the Cosmos service, you can start just using Postgres on a single VM with, say, a single core, but you can actually scale to large clusters of hundreds of nodes with thousands of cores. Kind of in an online fashion, you can have read replicas of your entire cluster in different regions, so you can scale to really large sizes. And we're trying to really scale relational workloads, so things that do joins and foreign keys and stored procedures and all the stuff people like to do with Postgres. And the way we do that is using the Citus extension, which is also open source. Actually, as of last June, it's fully open source. It used to be like 98% open source, but last year we fully open sourced it. And it's an extension that uses the hooks that Postgres provides to add the features of the ability to distribute a table or to replicate a table across a cluster of Postgres nodes that all have the Citus extension. And so when you do that, like first, we don't change Postgres, so we don't try to sort of auto-distribute. If you get to a server, you create a table, you just create a table on that server, but then you can choose to distribute it or choose to make it a reference table. And if you distribute it, it will transparently shard the data across your cluster. And you can also access the table from any of the nodes and do reads and writes. So your initial Postgres nodes, we call that the coordinator. For now, schema changes still have to go through the coordinator, but I think we'll resolve that. If you want to know more about the architecture, there's a Sigma 21 paper on Citus. So our job is basically to go through the Postgres manual, which is pretty massive. Probably if you print it, it easily reaches the ceiling here. There's really a lot of features, and we try to make those work seamlessly on distributed tables, including joins, transactions, sequences, expression indexes, and all sorts of fun features. But we also try to make them work well at scale, perform well at scale. That's probably the more challenging part. One thing that's quite important to Citus is the notion of co-location. So if you have two distributed tables that share a distribution key, we try to make sure that the same data is in the same place, such that if you join on that key, it's going to be a fast local join, or you can have foreign keys on that key. We also parallelize queries across the cluster. If you don't specify, let's say, a distribution key filter, or we explicitly route it to a particular shard to be able to scale transactions through. There's also gaps. I mean, I often say it takes about 20 years to build a distributed relational database that's any good. We're about 10 years in, but we can still solve some use cases pretty nicely. So scaling out relational data model doesn't make sense for kind of any arbitrary OLTP workload. There's a lot for which it doesn't make sense because of the relational aspect. Your data is like a cluttered lump where there's a lot of different relations, and every time you have to go over the network to evaluate a relationship, your database just gets really slow, and so scaling out can actually make things much slower. There's a few workload patterns for which it can work really well. For example, these kind of multi-tenant software as a service applications, where you've built maybe a fairly complex application that has complex joins and transactions and other stuff. But you're offering it to many different customers. That gives you a sort of natural sharding key in the customer ID. This is sort of an alternative to manual sharding that many companies have done, but having one database can make it much easier to manage. Another model is like CRUD applications that do really high, especially really high write throughputs, like high rate of inserts. So devices reporting their status, or people watching videos updating where you are in the stream, or telcos kind of tracking calls and how many bytes transferred, because that's how they do their billing. So that's, in that case, it makes sense to load balance those across different worker nodes. And also real-time analytics dashboards, where you kind of have a sort of continuous stream of data coming in, and you have a pretty high rate of analytical queries on that data, maybe hundreds per second, maybe thousands of seconds, because you have lots of customers looking at a dashboard and with different filters and different charts. So it's useful that you can combine kind of the ability to scale with also indexes to find recent data by certain criteria, but also joins to, for example, we see applications that these self-joins to do behavioral analytics, like users who first did this and then did that and then did that. So these are some workload patterns where Citus can work really well. What we also see is that because we've not actually used Postgres, we see a pattern emerging where users kind of, maybe they have an OLTP app with like 100 tables, and only one of them is actually really large. It's like a pretty common pattern. And there's, maybe you make that your distributed table. Maybe there's a few tables that table is joined with or has foreign keys to. Maybe those can be reference tables that are replicated everywhere. And the rest you just keep on one node, because why would you go through the trouble of trying to distribute it? If if you're an airline, you're never going to have a billion planes. Like your table of planes is always going to be pretty small. And this can work pretty well, because one thing we've learned over the years is relational workloads, are at least Postgres workloads, are pretty latency sensitive. And Postgres, there's this whole ecosystems of applications and client libraries, and they all have a kind of latency expectation. So if you have a database where, you find a row, you have a join, you find a row on the left, then you do some index block to find all the rows on the right, and there's several round trips involved in doing that, you can get pretty high response times. And typical applications, they're not very careful about using their database. So maybe this query is done in the context of a transaction that holds on to locks. So now you have a kind of serious concurrency problem that your locks are being held for a long time. But also the way the Postgres protocol works, it's interactive. Clients send a query, wait for a response, and send the next query. So while waiting, that session cannot do anything else. Whereas ORMs are pretty stupid usually. They do 10 queries in a transaction block, half of them do the same. But if all those queries take 100 milliseconds, then you have like one query per second per transaction. So it's actually pretty tricky to scale these types of workloads. So one of the things we do is try to pack related data that is going to be joined, it's going to have foreign keys together as much as possible, using collocation, using reference tables, using just a single node. And that's kind of necessary for scalability. Although it does create some burden on the user to make some choices around the data model. The other thing we've learned is there's no such mythical customer that says, I don't care if things are 10 times slower, at least it scales. Like the larger the scale requirements, the more cost conscious the customer is going to be, because it's, they see the number going up and they also realize they can save a lot of money. And so one thing we've avoided by just building extensions is to kind of try to redo the 30 years of engineering that went into making Postgres reasonably efficient for relational database workload. And in fact, instead, we just kind of rely on Postgres for a lot of things. Like if we have join that we know can be handled by a single node, or just give it to Postgres. It'll do its thing efficiently. It'll handle the concurrency efficiently, etc. And also, distributed Postgres doesn't make sense for arbitrary OLTP workloads, only for specific patterns, though hybrid models can kind of extend that a little bit. Another thing we learned is scalability is rarely really about raw transaction throughput, about going from 1,000 queries per second to 1,000,000 queries or beyond. What often happens is that applications are complex. I mean, they use Postgres because it's so versatile, so they're going to do lots of different things with the database. And they're going to have a small number of queries that at the beginning you don't even notice that they're there, but actually they're disproportionately affected by a growing database. So after a while, they're gobbling up the majority of the resources. And that's a large part of what scaling an OLTP workload is about, at least scaling a Postgres workload. The other thing is post development never stops. So we contribute a lot to Postgres and we build extensions. We don't fork, we don't try to rebuild it because it's almost impossible to keep up. There's one company that does a reasonable job of it. No one else has succeeded. after they fork Postgres. It works well the first 2 years. After that, you're just going to miss out on a lot of features and optimizations. And finally, developing a distributed relational L2P system is quite difficult because all the features in some ways relate to each other. They can be used concurrently. They can be used in the same transaction. They can be used often in the same query. They can be used in different layers of nesting of function calls. So that's lots of fun. And of course, it's a distributed system. So that's hard, but it's also a mission critical system because once you have your first customer in production, you cannot afford to lose a byte of data. So you have to be very cautious about how you do your software engineering. So, and that makes it a very slow process to build these kind of systems. All right, thank you. We're not currently hiring. Like many of the big companies, we have a hiring freeze, but we will at some point be hiring, hopefully this year. I'm based in Amsterdam. We have a team here. We have a team in Istanbul, Redmond, and San Francisco. If you have any questions, like you can shoot me an email or ask me here. I'm only here today, but I'll be around for today.
Thanks.